Okay, welcome, ladies and gentlemen, to our lesson 7.2. We're going to be finding areas in the plane. Obviously not an airplane. Okay, so we're going to be looking at calculating areas between two curves. And looking at a little bit new stuff for integration as well, integrating with respect to y. So that's our two big concepts for the day. All right, so the nerdy question. Have you ever wondered this question? You look at these two graphs and you go, hey, I really wonder how much area is between these two curves. And I know there's somebody out there that has. They're just wondering, like, how much shaded area is between these two curves right there? Well, it just so happens we can figure that out. And we could figure it out. You could probably figure it out pretty straightforward if you actually thought about it. Let's say that our blue function is f of x, and let's say our red function is g of x. Now we see that these two functions intersect at very specific points. Well, we could just call those 2 points something. We could call them A and B, just for general sakes. And if we were to think about we could just think about finding the area underneath F between A and B. Well, the area underneath F would look like this, between A and B. And we know how to find that using basic integrals, if we knew what the function's name was, what its equation was. And that would be the area underneath f of x. And we could also technically find the area underneath g of x. Well, the area under g of x would look like this. And you notice that they overlap one another, and that overlapping section is more than the area that's in between the two functions. And it just so happens that the area of f of x, or area underneath f of x, and the area underneath, or subtracted by the area of underneath g of x, is this area in between. So if we knew the 2 points of intersection, as we labeled them A and B, and their function rules, just meaning is it x squared plus 7 or whatever the name of the equation is, it's actually a very simple process. If f of x is greater than g of x throughout the entire interval from A to B, then the area between f of x and g of x from A to B is the integral of f of x minus g of x evaluated from A to B and written out in more symbolic terms that most of you understand. The integral from A to B of f of x minus g of x dx is this area in here between f of x and g of x. That's very, very simple. Now, there are ways that this problem can get a little bit more complicated. Let's say we wanted to find the area between f of x and g of x going from a to some c value over here. Well, we'd have to change this a little bit because then we'd want to do g of x minus f of x because the g of x function would be above the f of x. That's just a very specific example like this. But there's other things that can make this process a little bit more complex, and we'll see what that looks like here in just a few seconds. So let's go ahead and try one. I want to find the area of the region between the functions secant squared x and sine of x between the x values from 0 to pi fourths. And if you think about this graphically, pretty easy graphically, you can actually graph this on a calculator if you wanted to. From 0 to pi fourths, secant squared looks a little bit like this-ish, something like that. Kind of messed that up a little bit. And sine of x looks, well, we should know sine of x looks a little bit something like this. So this is secant squared x, this is sine of x, and we want to know the area here between the two functions. Well, because secant x or secant squared is above sine of x, we would like to take the integral of 0 to pi fourths of secant squared x minus sine of x dx. Well, that actually becomes a pretty simple problem. The integral of secant squared x is tangent of x, and the integral of sine of x is negative cosine, so this becomes plus cosine x evaluated from 0 to pi fourths. Tangent of pi fourths is 1, so we get 1 plus cosine of pi fourths is, oops, not pi, that's silly, root 2 over 2 minus tangent of 0 is 0, cosine of 0 is 1. So we get 1 plus root 2 over 2 minus 1. The 1's go away, we get an answer of root 2 over 2, which means the area in between these two functions is root 2 over 2, by the way, units squared, whatever it might be. See, pretty straightforward, pretty simple. Let's see a little bit something else here. Let's try this one. Let's try the area of the region enclosed by the parabola and the line y equals negative x. Well, let's see here. We kind of need to know what this means because notice in the first question, it gives you the index of integration or the limits of integration from 0 to pi fourths, but it doesn't give it to you here. So it's probably a good idea to graph the two functions, see what they're going to look like. All right, so the function y equals negative x looks like this basically. And actually, let's make that a different color. Let's make this red, going from here to here, negative x approximately. And let's go with blue for x squared or negative x squared plus 2. So we got to go to 2 and basically something like this. Well, if we want to know the area between the two functions, we're actually looking for this area here, between the blue and the red lines. Well, that means I need to know what value is this and what value is this. Where do they intersect? Intersection is pretty simple. We could do it algebraically. We could do it graphically. Just because it's right here, let's just do it algebraically. All we want to know is when the two functions are equal. So we go 2 minus x squared equals x. That means x squared minus x minus 2 equals 0. Oops, sorry, x squared plus x minus 2. So we get x plus 2 and x minus 1. And that means x is at negative 2. Oops, how did I factor wrong here? I don't think I did. Oh, yeah, I did. That's supposed to be a negative x. Haha. So I was right with my negative x to begin with. That's a negative x. Okay, change this up a little bit. All right, so that's equals to a negative x. There's negative x. That makes a negative 2 and a plus 1. That means x is, sorry about that, negative 1 and positive 2. That means our limit of integration now is going from x equals negative 1 to positive 2 of my function 2 minus x squared minus negative x. Right? My parabola minus my linear function because the parabola is above the linear function, dx. Well, if I just kind of simplify this a little bit to make this a little bit easier of a function to integrate, this would be negative x squared plus x plus 2 dx. And I get the very simple function, let's see, negative x to the third over 3 plus x squared over 2 plus 2x integrated or evaluated from, oops, not 0, -1 to 2. And you do the whole math here. If you plug in a 2, you get -8/3 plus 4/2 plus 4 minus 1/3 plus 1/2 plus, sorry, not plus, minus 2. And you simplify this all together, and you get 4.5 or 9/2. Don't worry, I did this all beforehand, so I already knew what the answer was. All right, so again, notice in this particular case, we were looking at two functions that we didn't know their intersections points at the time, but that were easily found. And after finding them, then we did our integration and found that the area between these two curves is 9/2 units squared. All right, what about this one? Find the area of the region in the first quadrant that is bounded above by the function y equals x to the half power and below by the x-axis and the line y equals x minus 2. So again, you're not always going to be able to see the graph, so it's a good idea to just graph the functions. So we go here, we get our two axes, and since we're looking at quadrant 1, I don't really need much rest of the graph. I really hope you do remember what x to the half power actually is. It's the square root of x. And the square root of x looks like this. The x-axis looks like this, obviously. And if I was to change colors here for the line y equals x minus 2, I'd be down here at -2, and it comes up here like so. All right. So again, we're going to need to figure out some stuff here. We could think about what point is this going to be here, what x value, what intersection value is this going to have. And you could probably pretty easily figure this out, that this is going to be the point 4,2. Now the question is, what are we going to integrate? Because technically this involves 3 lines. It involves the square root function, the linear function, and the x-axis. So in this particular example, what we're going to do is we're going to split this problem into 2 parts. I'm going to look at this first integration here. I can find the area between the square root function and the linear function by looking at this green area here, and I can look at this orange area as the area or the integral between the square root function and the x-axis, which actually is just the integral. So what we can do is we can say the integral, this is for the orange section, the integral from 0 to, we should probably figure out that this point is the point to 0. So from 0 to 2, we are just going to take the integral of the square root of x dx, which is just this little orange section. And then we want to take this orange section and this green section, so we're going to add the integral from 2 to 4 of the square root of x minus the x minus 2 function dx. So this is finding the area between the square root function and the blue line linear function here. Well, again, this just becomes some simple calculations. Doing the orange section, we get, make sure you're finding the antiderivative, not the derivative, that some of you guys keep doing. What would be the antiderivative of the square root of x? Hopefully you know how to do that. Well, we take x, we add 1 to the exponent, we get 3/2, and we multiply by its reciprocal, and that's evaluated from 0 to 2. And then we're going to add it to the function defined by this. This is, let's do this in green. 2/3 x to the 3/2 minus x squared over 2 plus, by the way, that's a minus and a minus, makes it a plus 2x evaluated from, not from 0, goofball, from 2 to 4. We do some very simple calculations, and we get area is equal to 10 over 3. Very, very simple. All right, but I'm going to hint at this. It's not the only way to do this particular problem. All right, so you may have seen something else to do here. It may not be the next thing we're going to do with this problem, but it might be another thing that we're going to do with this problem. All right, so let's think about this. Let's say this is 10/3. Let's go on to our next problem. What we're going to do now is we're going to try that same problem a little bit differently. So looking at that particular graph again, go red with that line, and we'll go blue. Oops, that's not supposed to be a line. Come on here. With the square root function again. All right, so we got to remember that this is the point 4,2. And what we're actually going to do here is something that's not exactly intuitive. But this is the new thing, the bigger new thing for today. Now, what we're going to do is we're going to solve both equations for x. And if we did that, the first equation here, let's call this the blue equation because that's the color I'm using. We will solve this for x, and we'll say that x is equal to y squared. Right, getting x by itself, just square both sides. And for the red equation, we're going to do the same thing. If we solve this for x, very simply, says x is equal to y plus 2. Now what you can think about is integrating, I'm sorry this is behind my picture here, but integrating with respect to y instead of x. So instead of thinking vertically this way, because that's what our mind is picturing, is vertically in kind of the way we want it to picture, we now have equations that are pictured with respect to y, so vertical is now this direction, which means when we're finding area now, we can find the area underneath the red line minus the area under the blue line will give me the total area again. So if we think about this as a red and blue statement, all right, so going from 0 to 2 in the y direction, we could find the area under red minus the area under the blue, which is here, and we will get this leftover area between the two curves. Now remember, we're integrating from 0 to 2 now because this is in the y direction. All right, so we look at this, we say the integral from 0 to 2 of y plus 2 minus y squared dy. We're looking at the y direction now. So this really just ends up becoming from 0 to 2 of negative y squared plus y plus 2 dy. And I get negative y cubed over 3 plus y squared over 2 plus 2y evaluated from 0 to 2. And I really hope I get the same thing as 10/3. Plugging in 2 actually becomes the only thing I need, because if I plug in 0, everything becomes 0 here. So plugging in 2, I'm going to do this a little bit over here, I get negative 8 over 3 plus 4 over 2 plus 4, and I get negative 8 over 3 plus, this is the same thing as 2, which is actually 6 over 3. And this becomes 12 over 3, which, lo and behold, this is 6 plus 12 is 18, minus 8 is 10 thirds. Yay, look at that, we got the same answer. Some of you are probably asking me, well, why are we doing this again? Well, it comes down to a choice. What version do you see is fastest for you? Okay? But what you're going to hate now is, was there another way that we could have done that particular problem that maybe didn't seem as intuitive? Or maybe it was intuitive, but you thought it was wrong. So let's think about that function again, or those two functions again. I know you're hating me right now because I'm saying let's do this over and over and over again. But let's think about it. I even drew it in the very first picture that we did. You just may not have seen it. So here's the square root function. Here is the line y equals x minus 2. And maybe you saw this. When I went and, let's see here. When I went and drew this dashed line down, maybe something clicked in your head. Maybe. And we know that this point was at 4. Well, maybe you saw this. If I was to find the area underneath this blue line, there was actually a subtraction that we could have done, and it had to do with geometry rather than calculus. Now, I love this because the book actually does this particular problem 3 times, and I actually liked it so much that that's why I particularly put this problem in here 3 different times. Because it ends up there were 3 different ways to solve the problem. One, with the very first intuition stuff that we're learning, taking area minus an area in calculus. Then it was changing it up a little bit with the derivative or the integral with respect to y, which again was calculus. But now we can do half calculus, half geometry. If we were to take the integral from 0 to 4 of the square root of x dx, and we said that this is let's say it's 3 halves times x to the 2 thirds, and that's evaluated from 0 to 4. I'm sorry, not 2 thirds, 3. Sorry, I've got my numbers backwards here. Let's try that again. Let's say it's actually to the 3 halves and the 2 thirds out front. Knew something was going to work there. If we plug in 0, it just becomes 0. So all the thing that matters is plugging in a 4. So it becomes 2 over 3 times 4 to the 3 halves. Well, the square root of 4 is 2. To the third is 8. Times 2 thirds is 16 over 3. But then the question is, that wasn't the answer we got. It should have been 10 thirds. But here's where the geometry comes in. The geometry says, oh, we could actually just take away this nice, lovely right triangle. If we knew the area of this right triangle, we could just take it away. Well, it's nice that we actually know that this intersection point is 2 and that the height is also 2, which means this is a 2 by 2 isosceles triangle. 2 times 2 is 4. So if we looked at this area as half times 2 base times height, I get 2. Well, 2 is the same thing as 6 over 3. And if I'm subtracting that 6 over 3, I get 10 thirds. And some of you, maybe your mind just got blown right there. We just did this problem 3 completely different ways, mostly with calculus, but with a little bit of geometry thrown in there as well. And you can use geometry wherever you need to. Let's say you need to take away the area of a circle. That's pretty simple. Pi r squared, by the way, if you didn't know that. All right, so let's kind of take this for what it is, and then let's go to our last problem. Just bear with me, it's not the same problem. So this is going to be our last problem for this video. And what I want to find is the area of the region enclosed by the graphs of y equals x cubed and x equals y squared minus 2. So this kind of throws you for a loop. And this is where it starts to come down to, I really hope you know what these functions look like. And obviously, a lot of the times you're going to have a graphing calculator, but what if you didn't? What if this comes up on a section where you're not allowed a graphing calculator? Well, then some of you are going to be like, oh, well, I'm screwed. But I hope that's not the case. So if I look at y equals x cubed, most of you know that this function looks like this, as well as I can draw it on this tablet. But some of you might not know what x equals y squared minus 2 looks like, and you're going to try to solve it for y and get only half of your answer. But this is just a quadratic function in terms of y instead of in terms of x, which means it's going to open to the right or open to the left. But because it's a positive y squared, it opens to the right. And since it's just a simple minus 2, that just means it opens like this. And my vertex is down here at -2 on the x-axis, not on the y-axis. Now that's actually pretty simple, but now we have some issues. What are we going to do? We do have some 2 intersection points, but if I wanted to find the area between these 2 curves, I'm looking for this area between here. But here's a problem. This intersection point doesn't occur at the farthest left, which means we will probably end up needing to find 2 areas and add them together, or there is a way we could do this in one fell swoop, one giant step here rather than 2 steps. The question is, the choices, I mean, it's not really a question, it's just which one do you want to do? What one suits you better? Now, with doing the 2 area versions, you will have to find the intercepts, by the way, and because I have chosen full textbook examples here, these intersection points are not that great. But let's call this, and I'm going to do this as the textbook does it, just because I think it's a very good way to do it. Let's call this the point AB, and this is the point CD, rather than going through the full legwork of doing this problem. Let's think about both of these problems as y equations. So the red equation is going to change to y equals the square root of x plus 2, but it's also equal to the negative square root of x plus 2, because when you add 2 and then take the square root of both sides, you have to have plus and minus. So if you were to try to graph this in your calculator, you would actually have to graph all 3 of these equations. So if you're using your calculator, this is what you're going to need. Now, we could do this. We could find the area between the red and the blue first, and then find this little area down here. And technically, that's not super challenging here. If we were to take the, let's see, how would we go about this? Not too bad. If we just took the integral of, let's go from A to C in the x directions, right? A to C of the square root of x plus 2 and minus x cubed dx. And then we would have to add the integral from -2 to a, right? From -2 to a of the square root of x plus 2 dx. Well, that would just give me this little area here, but because this is symmetric, we could actually just double that area and we'd be good. Now, less intuitively, and probably the easier problem, would be to find the area between these two functions as functions of y and do the integral with respect to y. So what I could do with my blue equation is change that into x equals the cube root of y. And then that way we can take the integral of this function, the blue function, minus the red function. So we would say the cube root of y, or the integral of the cube root of y, minus y squared minus 2 dy. But then you have to pay attention to your limits of integration. In this case, b is my smaller number in the y direction, so it's got to go from b to d in the y direction. And the CD, the AB, they're actually very easy to find. You might even know that this point is actually a very good point. But you can find that out on your calculator. Once you graph the things, you can find intersection points, all that sort of fun stuff. I'm actually going to leave it at this. If you were to do the calculator version, Math 9 would come out as an answer of 4.21. And you can actually type it in as the function y like this. You just tell it that the variable out here, they give you a little squared box here. You just tell it y, and it will take the integral with respect to y rather than with respect to x. So about 4.215 if you're rounding as an AP Calculus student should be rounding to the third decimal. All right, can we integrate? Sorry, I kind of asked these questions without even thinking. Could we integrate it with respect to y? Sure. Could we integrate it with respect to y? Yes. Can we? Of course. Do it anyway? Yes. So I want you to go forward now and find the areas underneath or between two curves. Have fun with it. This is actually pretty interesting. And it will start getting us into the next lesson involving volumes. All right, I will see you guys on Monday.